And now we're going to be doing problem 17 on the EE301 12-week review packet. This problem concerns a resonant circuit. So we'll get started with part A, which is to find the value of the inductor in millihenries if the resonant frequency is 1800 hertz. So if we look at our equation sheet, we'll notice that the equation for resonance frequency is 1 over 2 pi radical LC. Okay, so all we have to do is rearrange to solve for the inductive value. So that's L, right? So we multiply both sides by 2 pi, then we square both sides, and then we'll just switch the positions of L and C. You can see above the steps we would take. We'll have 1 over radical LC, and we would have 2 pi Fs over here. And then we would say, okay, now we'll square both sides. So we would have 2 pi Fs squared equals 1 over LC. And then we would just multiply both sides by L and then divide both sides by this term here. We would get L equals 1 over C 2 pi F squared. So now we just plug in the values. 1 over 2 pi 1800 squared, and that's times C. C being right here, 2 millifarads. And that would give us a value of roughly 3.91, and that is in millihenries. So that's our answer for A. Now B, calculate the reactance of the capacitor and the inductor. How do they compare? So what we'll do is we'll just plug them into the normal equations for reactance. XC is equal to 1 over 2 pi FC. So that's 1 over 2 pi 1800 to micro, which will give us 44.2 ohms. Now, inductive reactance is 2 pi FL. That's 2 pi 1800 L, which we found earlier is 3.91 milli. And that gives us, again, 44.2 ohms. They're the same value. And that's what resonant frequency is. You should have expected that, or when you're taking the exam, you should expect that in a resonant circuit. You should have the same inductive and capacitive reactance. The X values should be equal to each other at the resonance frequency. So the next step is to find the current magnitude at the resonance frequency. So let's find total impedance. We know that total impedance is going to be the impedance of all three of these elements put together. Luckily, we know that we have our R value, which is 4, right? And that's going to be an angle of 0. And we have J 44.2 minus J 44.2, right? Because the capacitor would be negative JX and the inductor would be positive JX. These are equal to each other, so they cancel out. And impedance is just 4 for the resistor. 4 at an angle of 0, if you prefer to write it that way. It doesn't make a difference. So when we put it into Ohm's law, we'll take the current. Remember, we're trying to find the RMS value. So what we'll do is we'll need to find the RMS value for the voltage first, right? So this is current equals voltage RMS over the impedance. So that will be 20 times 10 to the negative 3 over radical 2. And that value is roughly 14.14 times 10 to the negative 3. And that would be 14.14 millivolts. That's 10 times 10 to the negative 3 over 4. And that gives us 3.54 milliamps. And that would be our source current in RMS. Now, find the power dissipated by the circuit at resonance. So remember, because these are at resonance, they're going to cancel each other out. So all we need is P equals I squared R. That's 3.54 milli squared times R, which is 4. And that's going to be 50.13 microwatts. Remember, power is in watts. Real power is in watts. So the next step they want me to do is find the Q value of the circuit. So remember, Q is the reactive power. So calculate reactive power of the circuit and solve for the resulting bandwidth. So what we have here is we have QF, right? So I'm sorry, a Q in this case, I know this is a bit of the confusing part of this unit. This Q does not stand for reactive power, okay? If you look on your equation sheet and you go to the section at the bottom, which is series resonant circuits, you'll notice that there is a QS value. That is what they're referring to. It really should have been labeled here, QS of the circuit, okay? So that is used to find the bandwidth. And all we have to do is take the inductive reactance and divide it by the resistance. So that would be 44.2 at 4. And that would give us roughly 11.05. So remember that this right here, I know it's labeled as Q, which can be confusing because we just dealt with power, but it is Q subscript S, which you can find at the very bottom of your equation sheet. So before because I know you're probably thinking, oh, Q is 0 because when I add up the reactive power of both, but they're not referring to reactive power in this case. It was just mislabeled. So keep an eye out for that during the exam. Don't confuse Q with Q subscript S. They're different values. So your next step is just to take that and plug it into the bandwidth equation. BW is equal to the resonance frequency over QS. So that's 11.05 over 1800, which will give us roughly 162.9, and that is in hertz again. Bandwidth is in hertz. So our last question is, what is the cutoff frequency? Calculate the power dissipated by the circuit at these frequencies. So what we need to do is we need to figure out F1 and F2 for the circuit. And if we look at our equation sheet, we're given an equation for that. F1 and 2, oh, my apologies, my pen going a little crazy. F1 and 2 are equal to the resonance frequency plus or minus bandwidth divided by 2. And conceptually, that should make sense. Bandwidth is the difference between those two values. So if we cut it in half, then that should be the difference between the middle frequency, which is the cutoff frequency, and the upper and lower limit. So F2 is going to be our upper limit, which means we have to use a plus for it. So F2 is equal to Fs plus bandwidth over 2. Bandwidth over 2, so that's 1800 plus 162.9 over 2, which gives us 1881.5, and that's in hertz. F1 is our lower limit, which means we have to use a minus sign. So Fs minus bandwidth over 2 equals 1800 minus 162.9 over 2. And that gives us 1718.5 hertz. Finally, they want to know the power dissipated at the frequencies. So what we do is we take the circuits, and if you look at the equation sheet again, we'll notice we have a equation for the high pass filter, right, which is 1/2 the maximum power. So what we need to do is we need to find, we take our power we found here, power, and we'll say that's high pass filter. And we'll say that's 1/2 the power max, which we found in part D. So that would be 1/2 of 50.13 microwatts. Okay, and there we go. That is 225.06 microwatts. And this right here is actually a conceptual question. I know it seems like it's just like, oh, well, I just plug those values in. But what you're going to end up finding is that the power at both F1 and F2 is equal to 1/2 of the maximum power. So this is a conceptual thing. Power at F1, oh, sorry, that is super rough handwriting. Power at F1 and F2 is equal to 1/2 the power at the synchronous frequency or the resonant frequency. So that's basically how you solve for that. You could also just plug it in and resolve for the circuit, but your exam is a limited time evolution, so you're going to want to know this little fact here at the bottom. Power at the two cutoff frequencies, F1 and F2, is equal to 1/2 of the power at the resonant frequency. Okay, so write that down. I usually recommend having a note sheet that you have all these little tips on there, and before you go to the exam, you look it over so that right when you take the test, you have it in your brain. Of course, you can't look at it while you're in the exam, but there's nothing stopping you from looking over your notes right before the exam starts and taking in all these little tidbits that are going to help you on the exam. That way it's fresh in your brain while you're doing the problem. And if you really wanted to, you could scroll through the exam at the beginning when it's all fresh in your head, and you could write all these rules down. So you say, oh, there's a resonant circuit, right? So I'm going to write that rule down. That way, when I get to the problem, I'll still remember it. I won't have forgotten it during the exam. Just little tricks like that can help you out on a test. So that is problem number, what problem is this anyway? Problem number 17.